Hello everyone, I'm Chris McIntosh. I help teach the statistics courses. This week we're going to go over two-way ANOVA or factorial ANOVA. This is from chapter 14 of Navarro and Foxcroft of their text. So categorical variables that divide into groups are known as factors. Up to this point, we've identified variables with nominal or ordinal level of measurement as categorical variables. Another name for a categorical variable is a factor or a factorial variable. The ANOVA test can have more than one factor. An ANOVA with a single categorical variable or factor is called a one-way ANOVA. An ANOVA with two categorical variables is called a two-way ANOVA. You can have an ANOVA with three categorical variables, or even more. It would be called a three-way ANOVA. For all intents and purposes, this is the practical limit. Two-way ANOVA is fairly common in published literature. Three-way ANOVA is very rare in published literature. I've never personally run across anything more than a three-way ANOVA that's been published. We will see in upcoming slides that the more factors you analyze with a single ANOVA, the more complicated it is to understand and report the results. A two-way ANOVA looks at both factors. It is similar to running two separate one-way ANOVA tests. There's a difference, and we'll see that shortly. The next slide demonstrates what you might see for two factors with two levels each. You could see the same effect separately by running two separate one-way ANOVA tests. A two-way ANOVA looks at both factors. This chart, the figure looks at what might happen with two factors in a two-way ANOVA. The first factor, factor A, has the levels differentiated on the x-axis of the graph. The second factor, factor B, has the levels denoted by two separate lines, one dotted line and one solid line. In the top left corner, only factor A has an effect. The mean for level 2 is higher than the mean for level 1, so both lines slope up. In the top right corner, only factor B has an effect. The lines are separated because the values for the levels of factor B are different. In the bottom left corner, both factor A and factor B have an effect. The lines are separate and they change position on the graph. In the bottom right corner, neither factor A nor factor B has an effect. The lines are together and the value doesn't change on the graph. A two-way ANOVA shows the interaction between the factors. You can only see the interaction between two factors when you include them both in a two-way ANOVA. A one-way ANOVA doesn't show any interactions between the independent variable and any other variables. The main advantage of a two-way ANOVA over two separate one-way ANOVA tests is the ability to test the interaction between the two factors. A two-way ANOVA shows the interaction between the factors. This figure looks at what might happen with the interaction between two factors in a two-way ANOVA. The first factor, factor A, has the levels differentiated on the x-axis of the graph. The second factor, factor B, has the levels denoted by two separate lines, one dotted line and one solid line. In the top left corner, the values for one level of factor B increase between levels of factor A, while the values for the other level of factor B decrease between levels of factor A. The levels for factor B show differences to begin with, and they change differently. In the top right corner, both levels of factor B increase in regards to levels of factor A, but they don't increase by the same amount. The lines are not parallel. In the bottom left corner, one level of factor B increases while the other stays the same. In the bottom right corner, there's a difference in value between the two levels of factor B, and they change differently. You know there's an interaction between two factors when the lines are not parallel to each other. It's especially apparent when the lines cross each other. There's an interaction for every pairwise combination of factors added to the model. When you have two factors, you'll have one interaction between them, factor A, factor B, and the interaction between factors A and B. The two factors have one interaction. When you have three factors, you'll have an interaction between each pairwise combination, factor A, factor B, factor C, the interaction between factor A and factor B, the interaction between factor A and factor C, and the interaction between factor B and factor C. You'll also have an interaction between all of the independent variables at the same time. In this case, there's three independent variables, so you're going to have a three-way interaction between factor A, B, and C. In total, the three factors have four interactions. The more factors you add, the more interactions there are. Four factors would have all the two-way interactions, all of the three-way interactions, and the four-way interaction. This is why you never see anything higher than a three-way ANOVA published. Even a three-way ANOVA is difficult to understand. You want to check assumptions before interpreting results. Normality, you can use your eyeball test, look at the histogram, QQ plot, or the Shapiro-Wilk or Kolmogorov-Smirnov test. And again, with normality, skew is more important than kurtosis. For homogeneity of variance, we can look at Levine's test. What are all the alternatives if our two-way ANOVA assumptions are violated? For normality, there is no non-parametric equivalent for a two-way ANOVA. So you would have to use the non-parametric equivalent for a one-way ANOVA, which is the Kruskal-Wallis test, for each factor separately. You can use robust methods. We're not talking about those in this class, but I just want you to know that is an option. Homogeneity of variance, again, you're down to separate Kruskal-Wallis tests for each factor separately, or using robust methods. If you are ambitious enough to try a two-way ANOVA, then I would suggest having a statistician check your results and your write-up. But a basic plan for writing that up would be to state the purpose and the factors, report a significant interaction first, report main effects, each factor separately, like one-way ANOVA, and describe the nature of the interaction, provide the interaction plot. I'm going to go back to the interaction slide, and I just want to emphasize to you guys, for a two-way ANOVA, the very first thing when interpreting results that you should look at is the interaction, and we're going to see what that looks like in the computer assignment. But the main thing, the main point of a two-way ANOVA is to see, is there an interaction between these two independent variables? If there is a significant interaction, then pretty much the main thing you need to do is explain what that interaction looks like. And we're going to see an example of that in the computer assignment. But I just want to emphasize to you guys that really that interaction is the key. If it's not significant, then you just report each main effect or each factor separately, like it was a one-way ANOVA. But if it is a significant interaction, then you're really going to focus on explaining what that interaction looks like for the reader, because you need to be careful about interpreting the one-way, the individual independent variables without explaining that factor. And we'll look at the steps for this for a two-way ANOVA in the computer assignment. And that's it. Have a good week.